if there's no friction still, so if we have a ramp like this, we place a ball on it, but there is no friction, then nothing different happens here than whether it was a block. A block would just slide, this would just slide. There's no reason for this to turn. The thing you need to remember, the thing that needs to be prominent in your notes here, is that the only way an object will go from not moving to moving is if there's an unbalanced force or an unbalanced torque. I'll say it again, the only way something goes from not moving to moving is if there's an unbalanced force or an unbalanced torque. If there's no friction here, there's still an unbalanced force, which is why it will slide down the ramp. But there's no unbalanced torque, so it doesn't roll, it doesn't spin. Again, there's no friction, so because there's no friction, there's still an unbalanced force because it's on a ramp. But there's no unbalanced torque, so it will slide, but it won't begin to spin. If there is some friction, that doesn't automatically mean the object is going to roll. I'll say that again. If there is some friction there, it doesn't automatically mean the object's going to roll. It could still slide. You see, there's going to be three forces acting on the object at that instant, at that point of contact. Remember, we're dealing with torques now, so the point of contact matters. So there's the obvious force, gravity acting downwards. There's the next force, normal force, acting upwards. But we're drawing them now at their point of contact, which is going to become more and more important as this discussion goes on. And there's going to be friction. Now, I don't think it's hard to recognize what direction friction will be in this circumstance, but just let's make sure, what direction do you think I should draw the frictional force? So, when considering the frictional force, you should ask yourself, well, how is the spin of the object going to change? That will help you draw in the frictional force. So these are the three forces that are acting on the object: weight, friction, normal force. Now, for the object to change its motion, there has to be an unbalanced force. We have two forces that act in the x direction. Good morning. Thank you. We have two forces that act in the x direction. You should be able to write them into a net force equals ma kind of thing. Would you try real quick? Because you know things. And I'm specifically talking about the x direction here. So when I call on you in a minute, you'll be able to tell me. I'll put you on the spot, get you all confused right before your stat test. No pressure. My disappointment can't be expressed as much as it should be. So you should prepare for like a big review set of homework to go home sometime in the next day or so that has just the basic force stuff on it, since apparently you don't remember any of it. Mg sine theta, like we talked about yesterday, minus friction equals ma. That's it. We did half of that yesterday. You just had to add the minus f here. I had all sorts of weird stuff out there, but we did this yesterday. I mean, just yesterday, as I recall. I hasten to ask, but can you do the y direction? One would hope. So, I don't feel like making the trip through the room because, yikes, I'm very disappointed. If I want this kind of disappointment, I'd teach middle school. Ha 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 ha. These are all old school things from first semester. Now, here's where, I wanted to get to the nuance, but I'm apparently having to kind of bludgeon you with the big picture things. Let's talk about the nuance now for just a minute. Although this is just getting us started, we're trying to ask the question, does the object slide or roll? And that's an important distinction because that determines whether we're talking about kinetic friction or static friction. And we know that there's differences between these. Whether an object rolls or not is based on a simple principle or a single principle. For an object to roll, this point has to remain at rest relative to the surface. I'm not going to repeat myself a bunch, but you guys don't know things, you should know that. So do I need to repeat myself like 5 times, or can you just write that down? For an object to roll, that point has to be at rest. The point of the circle, right? The thing that is rolling has to be at rest relative to this point right here. Otherwise, it's sliding. I'm bringing this up because things sometimes have to transition from sliding to rolling. If you've ever thrown a bowling ball, it slides for a lot of the alley, but maybe starts to roll towards the end. It might be spinning and moving, but it is not necessarily rolling. Rolling is a very specific circumstance. For something to be rolling, this condition has to be true. Right? We've seen that condition before, but for something to be rolling, that has to be true. And rolling means that this point is instantaneously at rest with respect to the surface. That's how we say it. That's how it will be described, say on a test. Instantaneously at rest, because this point is only in contact for an instant before the object has turned and a different point is now in contact. So we are freezing this a moment in time as it's rolling. Moreover, and this is the part that I wanted to add to I was hoping that you guys could produce this on your own today after yesterday's mental jog. The fact that you couldn't makes me sad, because what we have to do next is a little more challenging. We have to recognize that something else is happening at the same time, that there is an unbalanced torque acting on the system. Now, this part's a little more complicated. And I want you to consider that because it's a little more complicated, I'm going to explain it 2 different ways. You can think of rolling in 2 different ways. The first way is that you can think of rolling as an unbalanced force with respect to the center of the circle. That the object is spinning about this center. I think that's how most people think about rolling. That's not really what's happening, but I think that's how most people think about rolling. So when we talk about something that's rolling, this is still happening, but also there is a torque due to friction. Now, if you remember how we deal with torque, R dot F dot sine of an angle. From the picture, the torque arm would have to be this distance, right? Because the friction is acting at the bottom edge, and the force would be the frictional force here. So our torque would be R dot friction equals I alpha. And that's how we would deal with it. Moreover, we'd probably say R dot friction equals I. If this is true, then we know from earlier that this would have to be true. Right? We did that last week, well, before spring break. So we get something that looks kind of like this. I'm putting the R squared there because if you remember anything from before spring break, everything that rolls has an r squared in it. You remember all of those things, like the hoop and the disc and all of that? So we know the r squared will eventually cancel out when we put in there what the shape is, whether it's a solid sphere or a disc or a ball or something. But I want to caution you, what's actually happening isn't this. This is okay. You can use this. This works. Mathematically, this is just fine. But that's not really how things roll. So I want to make sure in your notes you have the real thing of what's happening. So this is a mathematically accurate representation. So this is accurate and will work. But truthfully, that's not what's happening. What's really happening is this point is the point that's at rest. So that's the actual pivot point. So when things are rolling, they pivot about this point that's not moving. Which means, based on that pivot point, it isn't friction that's causing it to spin. Because friction is acting at the pivot point. And because of that, it doesn't cause a torque. I would write all of those things down, because I don't think you would know them. And I know that they're just words, but you know on tests how I tend to want you to write things down in words, right? So the actual pivot point is the point of contact. That's what's really happening when something rolls. The actual pivot point is the point of contact. Because that's the actual pivot point, friction doesn't cause a torque. Instead, friction holds that point in place. Instead, friction holds that point in place. The real torque is caused by gravity. That's the torque arm. It's from the pivot point to the one force that's causing a torque, gravity. So the real mathematics of this deal with gravity and this angle. Now luckily that angle is the same angle as the ramp. So that will still be whatever theta is for the ramp. But when we look at a torque relationship, which I need you to be able to do, I would have to say net torque equals I alpha. But this time things are more complicated a little bit, because my torque, R times F times the sine of the angle, will be R times mg times the sine of theta. The other problem is more complicated in that I has to use the parallel axis theorem. Do you remember talk of the parallel axis theorem? Because we're not spinning this about its center anymore. We're spinning it at a point about its edge. We still get to use A over R, however. That's still just fine. Now that's what's actually happening. And although it looks more complicated, the truth is, once you put in the parallel axis theorem, using this method is actually faster in solving the problem. But it's more complicated to set up. So you can choose either one of these as your way of analyzing an object that rolls. I would encourage you, though, to not forget, you only need one of them. So either this one or this one is the only one you need. But you need one of them, but you still need this stuff. Now, the big picture here, and what is missing, is that an object that rolls has friction, but needs static friction to roll. It's not sliding. That point is instantaneously at rest with respect to the surface. So it takes static friction to roll. And static friction is an inequality, if you'll remember from first semester. usually objects don't take very much friction to roll. This is an inequality, but it's usually at the very bottom end of that inequality. You can never use this to figure out how much friction there is for an object that's rolling, because it will always be well below the threshold unless your angle gets really, really big for some reason. So this can only tell you limits of how something rolls. It really can't tell you much about the friction for how something rolls. Either way, I want you to notice that we could, starting from here, figure out the acceleration, just like from yesterday. We just do a substitution. This will tell us how it accelerates. We didn't have this yesterday because there wasn't friction. We were just talking about the box sliding down the ramp. But for an object that rolls, we have to find a way to eliminate friction to figure this out. And that's how we would do it. We would do that substitution. So I would get mg sine theta minus I over r squared times a equals ma. So if we're analyzing something that's rolling, I'm going to just put all the stuff on the side there. Did you see what I did? I moved this over to the other side, and then I factored out the a's. Do you guys all see that okay? I want you to notice that this is the unbalanced force. This now represents the inertia of the system, and A. Just like before, net force equals ma. It always is going to work out sometime. The difference is there's more inertia here. And do you see that there's more inertia? The number's bigger because we have to include not only the object's translational inertia, but we have to include its rotational inertia too. Things that roll have more inertia because we're overcoming both kinds of inertia. More to the point, look at this part. If the moment of inertia is bigger, it's harder for that object to turn, which means it's going to accelerate less. So let's consider doing two things here. You guys know things. A disk has a moment of inertia of 1/2 mr squared, and a hoop has a moment of inertia of mr squared. So remember when I rolled the disk and the hoop across the desk? Well, that's this problem. Let's look at the difference between the two. So let's do the disk first. mg sine theta equals, all right, in the parentheses, I have I in the numerator there, 1/2 mr squared divided by r squared plus m all times a. Everybody see what I did? I replaced the I with 1/2 mr squared. Do you notice that the r squareds go away? So mg sine theta equals 1/2 m plus m times a. In fact, if I just add those up, we'll leave that there for a second. The hoop, mg sine theta equals, all right, up here in the parentheses, mr squared divided by r squared plus m times a. Just comparing the hoop and the disk. So mg sine theta, cancel the r's, get m plus m. Add it together. Now, we're trying to compare the two, right? So I'm going to go ahead and simplify. Just cancel out the m's and divide by 2. Same on this side. Cancel out the m's. Multiply by 2/3. Is it clear that 2/3 is bigger than 1/2? Now all we did was prove that the disc will roll faster than the ring. It will get up to speed sooner. Now, if we put the box there, like if we replace it and look at the box there, the box could slide if the friction wasn't so great that it would slide, right? Because things can slide down a ramp if there's not enough friction. But there would be friction there on the box, right? So if we replace the ball and put the box there, we'd have to deal with friction. The difference is if we put the box there, it wouldn't be static friction, it'd be kinetic friction, right? A different kind of friction. And as it slides, that frictional force is taking energy away from the system because it's doing work. It's doing work against the motion of the box. Do you remember the definition of work from first semester? Oh my word. Does anybody remember the definition of work? It's like I didn't even teach anything. Nate's trying to say something, but he's being very quiet. Oh, feels like middle school all over again. All right, so you have an equation sheet. I'll give you a second. Somebody, work equals a force times a distance times the cosine of the angle. That's right, thank you. So this is the way you calculate work done by a force. If the box is sliding down the ramp, I would say that this would be the displacement of the box. And the force is acting this way, right? Friction. So can we all agree that friction and the displacement have an angle of 180 degrees? All right, lots of good stuff there. Oh, it's hurting my heart. So the work would be negative by friction, right? Because it would be F times D times the cosine of 180 degrees. All the things we talked about first semester. I'm just desperately hoping you remember something. I would be prepared for some questions like this, like early in the week next week, just to jog your memory. That would make this negative, and that means that friction takes work away from the system. That's why I brought it. That's why I'm bringing it up. If the box is sliding down the ramp, what we're used to is friction is something that takes away energy. Because I want to talk about this new situation, but I have to have you guys know a little bit about the old situation first. Because you might be led to believe that, well, friction's acting on the rolling object. Is it taking energy away from it? Well, this object's not sliding. This point right here is instantaneously at rest. This is static friction. This frictional force isn't taking energy out of the system because the point's not sliding, so it's not doing work in that manner. It is causing the object to roll. In the case of an object that's rolling, and again, things that I think you should know in your notes is what I'm about to say, a banner idea, a thing that should be important, like a little bullet point next to it. I'm trying to help you take your notes. You're not getting a PowerPoint from me. You're supposed to organize yourself. This is college. So here we go. There are two forces doing work here. There's the weight, obviously, pulling the object down the ramp. It's clearly doing work. And it's doing positive work because there's a component of the force in the direction of motion. So the weight does positive work because there's a component of the force in the direction of motion. I tried to put this analogy together for you, but it's been hard. So help me out here. If I wanted to translate work for all of the things that we've talked about for rotation, what would we replace force with? Torque. What would we replace displacement with? What's the rotational version of displacement? Sure, so we're going to use delta theta. Now this theta is going to be confused with that theta. So instead of making it confused, we're just going to leave the angle part off because our our forces are always doing work differently for rotation. We don't worry about the angle because it's a torque. Torque has angle in it already. You follow what I mean? Torque has the sign in it, already has an angle in it, so I don't have to worry about the angle part. This is rotational work. Friction is doing rotational work, and it's in the direction of motion. So unlike something that slides, something that rolls uses the friction to do positive work. I'm going to say that again because I want you to have the big picture on this. Unlike something that slides, something that rolls uses friction to do positive work. It is adding energy to the system. It's a different kind of energy. It's rotational energy, but it's adding energy to the system. So everything we talked about today regarding an object that's rolling down a ramp was about forces. And in the end, we came up with an expression for how two different objects would accelerate when rolling down the ramp. And this took longer than I anticipated. So I want to point out there was another way to figure out what the object or how the object makes it to the bottom of the ramp too. Do you remember from yesterday? What's the other way that we could deal with this? Go ahead. Sure, we could compare the energies. So consider, and I'm just going to a new screen because, I want all the colors to be consistent. A new screen. To get away from all the force talk. So if I start the object at the top of the ramp, what kind of energy would it have? Sure, potential, MGH. When it makes it to the bottom of the ramp, if there's friction, the object's going to have both a linear velocity and a rotational velocity. And if there's enough friction and it's rolling, we know that the velocity is linked together. So there will be two kinds of energy at the bottom. There'll be rotational kinetic energy and translational kinetic energy. Now, we know a little bit about these, right? 1/2 mv squared for translational kinetic energy. How do we calculate rotational kinetic energy? Replace the m with what? Okay, replace the m with I, and what do we replace the v with? It's like pulling teeth around here. You guys should be two different forms of energy now. It has both of these. Right? There'll be both forms of energy. So if we're trying to do the problem like we did yesterday, we'd have to say that mgh equals 1/2 mv squared plus 1/2 I omega squared. Again, follow the whole line of reasoning with me, please. I'm desperate for it. We can replace the omega. And if I want to know how fast the object is going at the bottom, I could put them both in terms of v, because the object is rolling. So 1/2 mv squared plus 1/2 m v over r, not m, sorry, I, v over r squared. I'm going to keep going just like we did a minute ago. I'm going to move some things around here. 1/2 mv squared plus 1/2 I over r squared v squared. Do you see where I'm going with this, maybe? Like just a minute ago? So equals, I'm going to factor out the 1/2 in the front and get m plus I over r squared, and then factor out the v squared on the other side. So an object that rolls, it's generally going to be going a little slower depending on how much inertia it has. All right.